Welcome back. So as one might expect, I forgot a few little details that about measures and about the Lebesgue measure that I mentioned last time that I think I'd like to talk about. Um, uh, so okay, so first for arbitrary measures, there's some properties that these have which weren't. So I think I did things this way. I talked about measure spaces. Okay. And so measures have a couple of properties which are useful. The first is that they have the monotonicity property of an outer measure. That's not included in the assumptions of a measure, but it's it is a property that measures have. So if A and B are sets in the sigma algebra, and if A is in B, then mu A is less than or equal to mu B. Okay, so this is a property you'd like to have, and it's true. Another useful couple of useful facts for sort of sometimes calculating the measure of a set is the following. So if AJ are such that AJ is contained in AJ plus 1. Okay, so this is an increasing sequence of sets. And then the measure of the union okay, so this union is like an increasing union, right? So really, the union from j equals 1 to n is just an because of the increasing nature, and so what you would expect might be true and is true is that this measure is just the limit as j goes to infinity aj. Okay, because of this increasing nature of the size of the sets. Okay, good. Another kind of similar property has to do with decreasing sequences of sets. So if AJ again, so sorry, these are in A. Okay. So if so now the sets are going the other way around. So okay, so these decrease in size. And here I need to add an additional condition that at least one of these sets has finite measure. Then you have a similar sort of property as in the previous situation, except for intersections. So mu of intersection j equals 1 to infinity j is equal to is j equals to infinity mu. Okay. All right. Okay, so this is sort of approximating sets from the inside. So, the union, we're filling out the union of these sets with, finite unions. And here we're approximating these sets from the outside, right? So we take this intersection and then we, take the measures of the sets that contain it and that sort of shrink down to the size of the intersection. Okay, and so rather related to these last two properties and having to do with Lebesgue measure is okay. All right, so now we're going to say two comments that are specific just to the Lebesgue measure. So we're talking about the Lebesgue measure on R with the Lebesgue measurable sets, which we talked about last time, and then the Lebesgue measure lambda. Okay, and then the properties we have here is that if A is Lebesgue measurable, then the Lebesgue measure of A is the inf of the Lebesgue measure of sets O, so that A is contained in O and O is open. Okay, so the idea here is that you consider all open sets that contain A, and you take the infimum of the Lebesgue measure of those. So the idea is you can think of these open sets O as kind of shrinking to wrap up the set A, and the Lebesgue measure has this particular property. So it's a property that's similar to this one, but it just tells us that we can restrict our open sets to be open. So this is a particular property of the Lebesgue measure, and it's a particular property of a class of measures that can be defined on certain kinds of sets, namely those that are locally compact. Okay, and in a similar vein, going from the inside now, we can take the Lebesgue measure of a set A will be the sup of lambda of K, where K is contained in A and K is compact. Okay, so the idea is similar to this. Now we're kind of going to imagine taking our compact sets K that are contained in A and growing them to fill out A, and then the Lebesgue measure will be the sup of all such things. Okay. All right. Now, these last two properties indicate that there should be some special features of the Lebesgue measure with respect to the topology of R. So we're using the open sets here and the compact sets here, and one way of coming to an understanding of that is to consider a special class of Lebesgue measurable sets, and those sets are called Borel sets. So let's talk about Borel sets. So the idea of Borel sets is what we're going to do. So Lebesgue measurable sets in general are kind of hard to get your hands on. And what we're going to do then is we're going to build a collection of Lebesgue measurable sets, subsets of R, that are, somehow we imagine easier to understand. And so what it's going to show, first of all, is it's going to show that there's quite a lot of these sets. Okay, and that there's quite a lot of them that are relatively easy to describe. Okay, so these are going to be the Borel sets. Okay. So fact. Let's start out with a fact, a general fact. If we take some subset S, so if X is a set, and if let's say we take some collection of subsets script S, that's supposed to be a script S contained in the power set of X, so S is some collection of subsets. So then there is a smallest sigma algebra. Sigma of S that contains the sets from S. Okay. And the way you can kind of prove this is first by noticing that there exists some sigma algebra which contains S, namely the power set. Okay, and then you make the observation that if you intersect two sigma algebras that contain S, the result will be a sigma algebra that contains S. Okay, and so then you argue by that process that there's a smallest one. Okay, which by which is just the intersection of all of them. Okay, so then you need to show that that intersection of all of them is a sigma algebra, and of course that it contains S, and that any other sigma algebra which contains S is contained in the intersection. So that last part is pretty much tautologically true, but the other things you can prove relatively easily. Okay, and so we call sigma S the sigma algebra generated by S. Okay, so this is a way of starting with some sets that you might like, and building from that a natural sigma algebra that contains those sets. All right. So this will enable us to make this definition. So the Borel sigma algebra is the sigma algebra generated by the open sets. Okay, and so we denote by B of R, the Borel sigma algebra. Okay, and a set B in, oops, it's a bad looking script B. A set B from the Borel sigma algebra is called the Borel set. Okay, now you can think this isn't, really according to what I talked about here. This isn't really how you construct the Borel sigma algebra, but it's beneficial to think of the Borel sigma algebra maybe as arising in this way. Okay, to think of the Borel sigma algebra. I start with the open sets. Okay, because I know that the open sets have to be in the Borel sigma algebra. That's the definition of being generated by the open subsets of R. Okay, now complements of open sets. Okay, and of course, complements of open sets are closed sets. Are then also Borel sets. Okay. Right, and that's just using the property of sigma algebra. So if a sigma algebra, as we saw last time, has the property that if a set is in there, then so is its complement. Okay, so if the open sets are in the Borel sigma algebra, so too must be the closed sets. Okay, so then we can take countable unions of open, sorry, and not only just unions, but also intersections, may as well include those. Okay, although as we saw, the fact that countable intersections are contained in a sigma algebra is just a result of the fact that countable unions are, along with the complementation property. But let's just include that explicitly since we're not really trying to prove anything here. We're just trying to get an idea of what the Borel sets look like. Okay, so we can take countable unions and intersections of closed or open sets. Okay, and all of these are going to be Borel. Okay, so then you can you can continue in this way, and you can construct a large family of sets. Okay, so take complements, then take countable unions and intersections, take complements, countable unions and intersections, and so on. Okay, and so for the purposes of what we're interested in, we don't have to dig very deeply into that sort of iterative construction to get all the kinds of subsets that we're going to want that are going to be Borel sets. So let's just see how this works. Okay. All right. So first of all intervals are Borel. Okay, so certainly the closed and open intervals are Borel sets, okay, because of the way I constructed or thought about building up the family of Borel sets up here. Okay, but then you should also think about the intervals which are neither closed nor open. Okay, so for example, A, B. Okay, so that is equal to A union A, B. Okay, and this is closed. This is open. Okay, and so a union of and so each of these, the point is a Borel set. Okay, and so their union must also be a Borel set. Okay, so all intervals are Borel sets. Q is a Borel set. Okay. And why is that? That is for the following reason. So write Q as some countable collection of Q's like so. Okay. Note that each of the singletons, Qj, is closed. And so Borel for each j. Okay. And so therefore, the union of all the Q's, which is just the union of these singletons, is a countable union, is Borel. Okay. And the irrational numbers are also a Borel set. Okay, and just by the very way I've written it, it's Borel, because this is Borel, it's open. And so sigma algebras are closed under taking complements. And so the complement of this Borel set must be a Borel set. Okay. All right, so you can see then you can maybe convince yourself that you can build a pretty extravagant collection of Borel sets in this way. Okay. Now, let me list a bunch of facts about Borel sets and their relationship to Lebesgue measurable sets. Okay, the first fact I'm going to state is that all Borel sets are Lebesgue measurable. Okay, and in fact, this containment is strict. Okay, so I'm saying two things here. I'm saying that, first of all, every Borel set is Lebesgue measurable, and I'm also saying that there exist Lebesgue measurable sets that are not Borel sets. Okay. All right. However, although there are Lebesgue measurable sets that are not Borel sets, if A is a Lebesgue measurable set, then there exists a Borel set B and a set Z in R with lambda of Z equals 0. Okay, so Z has measure 0, such that A is equal to B union Z. Okay. All right, so what this is saying is that while not every Lebesgue measurable set is a Borel set, it differs from a Borel set by at most a set with measure 0. Okay, so it's almost true that every Lebesgue measurable set is Borel. Okay, so the way to think about what I'm doing here is that this is good news. That's not such good news. This seems to be better news, sort of recovering from the fact that not every Lebesgue measurable set is Borel. And then we'll close off with some bad news. Okay, and that is how many Borel sets are there and how many Lebesgue measurable sets are there? Okay, so what's the cardinality of the Borel sets? Okay, well, the cardinality of the Borel sets is the same, it turns out. So you have to do some, work to show this for sure. Is the same as the cardinality of R. So there are as many Borel sets as there are real numbers. Okay. And on the other hand, the cardinality of the Lebesgue measurable sets is the cardinality of the subsets of R. Okay, and this is to, if you do some cardinal arithmetic, okay, and this number is a lot bigger than the cardinality of R. It's the idea, okay? So the idea is there are many more Lebesgue measurable sets than there are Borel sets. But what the previous statement is that somehow there's a lot more of these Lebesgue measurable sets, but they're all measure zero. Okay. And so we have this sort of complicated interaction between Borel sets and Lebesgue measurable sets. But Borel sets are easier to kind of get your hands on, and so sometimes it's easier to work with them instead of Lebesgue measurable sets. Sometimes you want to work with the real thing, which you have to include these additional Lebesgue measurable sets that measure zero. Okay. All right. And so now you might wonder. So last time I said that first of all, that there are subsets that are not Lebesgue measurable. Okay, and those non-Lebesgue measurable sets are, kind of difficult to describe in the sense that it's hard to get your hands on them, and so that they tend to kind of be in some way pathological, and so you kind of in your mind you think of things in here that are as being kind of not pathological, but how hard is it to describe a Lebesgue measurable set that's not Borel measurable? Okay, well, it's not that easy. Okay, so it's going to be some subset of measure zero by this property here, or it's going to be a Borel set union with a set of measure zero. So you may as well just restrict to the measure zero part. Okay, and it's actually not that much easier to describe the way in which Borel sets are contained in here. So in other words, to provide an explicit example of a Lebesgue measurable set that's not Borel measurable. Okay, but these are things that won't really concern us very much. Okay. All right, so let's sort of wrap up our discussion of Lebesgue measure and talk about some terminology that's going to come up for us as we go through the rest of the course. A property P of the set of real numbers holds, and the terminology is almost everywhere, okay, if the Lebesgue measure of the set of points x in R for which P is not true, if that set has zero measure. Okay, so it's almost always true that P holds for a number x. Okay, so for example, the property P of X equals true if X is irrational, and false if X is rational. All right, holds almost everywhere. Okay, because we showed that the rational numbers being countable have measure 0. Okay, and so therefore the irrationals, the complement, does not have measure 0. All right, so this is a common terminology when talking about things in measure theory to say that something's true almost everywhere. Okay. All right, so that, as I said, sort of, I believe, finishes what we're going to say about Lebesgue measure. Now let's talk about the Lebesgue integral. Okay. All right. And so we're going to talk about the Lebesgue integral over I, an interval I. So it's already going to be a little bit different from how we did things with the Riemann integral, where we started with defining the Riemann integral and Riemann integrability over for bounded functions on compact intervals. Okay, so we do things a little bit differently. Okay, so let L of I be, L of I be the intersection with I of Lebesgue measurable subsets of R. Okay, so we think of these as being Lebesgue measurable subsets of I, is how you want to think about that. Okay. All right. So we need a property of functions that we're going to integrate. Okay, and so as I said, when we defined Riemann integrability, we started by our constructions by considering bounded functions on compact intervals, and we saw that it's not always the case that such a function is Riemann integrable, but we need to kind of start with a class of functions that you're going to try to integrate. Okay, and it turns out that this class it's kind of a peculiar definition, but let me give it. All right, so let F be, and we're going to allow functions here when we integrate them to possibly take infinite or negative infinite values. Okay, so they're going to take values in the extended real. It's not that you generally encounter such functions in real life, but you do counter them as limits. Okay, so you may have a function, a sequence of functions that becomes increasingly larger at some collection of points, right? And so you want to maybe include the pointwise limit of those functions by allowing the value to be infinity at certain points. Okay, so it's convenient to allow functions to take values in the extended reals. Okay. Okay, so then F is what's called Lebesgue measurable as a function. Okay, so we had Lebesgue measurable sets. Now we're talking about Lebesgue measurable functions. Okay, and the definition is this. Okay, so you take any A and R, and then you take the pre-image of this set A to infinity, including infinity, because we are working with the extended reals. And so this is going to be the set of points x in I, so that f of x is in here. Okay, so that's just what I mean by pre-image up there. Okay, so it's certainly not the inverse of f, right? Because f is generally not invertible, so it's a pre-image, not inverse. Okay, so it's just a set of points in I that map into here. All right, good. And the definition is that this set is Lebesgue measurable on I. Okay, that's the definition of a function to be Lebesgue measurable. Okay. All right, so that seems like a rather unmotivated definition. Okay, and it's because, so this is very often the definition that you will encounter. All right, and it's a definition that's kind of arrived at by a process, and it's kind of the simplest version that captures a more interesting phenomenon. Okay, so let me say some things about this definition. Oops, facts. So first, there's nothing magic about using intervals. So we're using intervals here, okay, but possibly extending off to infinity, or as we'll see, possibly minus infinity. And so there's nothing magic about using this particular semi-infinite integral. Okay, we could have used open there, and we could also have gone from minus infinity to some b. Okay, so we could also have used A infinity minus infinity b, or minus infinity b in the definition. Okay. All right, so and that's sort of a matter of understanding. It boils down to the fact that the complement of a Lebesgue measurable set is also Lebesgue measurable. Okay, so for example, this is the complement of that. All right, so that's more or less what it comes down to. Okay. So one of the reasons this definition is complicated is exactly the requirement that I allow functions with possibly infinite values. If I relax that and only consider real valued things, then the definition becomes a little bit simpler. Then f is Lebesgue measurable if and only if f inverse, okay, of a Borel set is in for every b in set of Borel sets. Okay. So first, let's make sure we understand what this is saying. Okay, so I have now a regular real valued function. And so rather than taking pre-images of sets like this, and so you see here, that one of the differences is the possibility of including infinity here. Borel sets, so this isn't in I, this is in R. Oops. Okay, so Borel sets, are subsets of R, so they don't include infinity, all right? And so by relaxing the need to include plus and minus infinity, I end up with a simpler characterization here. And so the pre-image is taken not over these weird intervals, but over Borel sets. Okay, so the pre-image of every Borel set is a Borel set. Oh, sorry, is a Lebesgue measurable set. Okay, so first let's think about why this is true. What is the Borel sigma algebra? Well, the Borel sigma algebra is generated by the open sets, okay? But it turns out that the Borel sigma algebra is also generated by intervals, okay? And it can be generated by these intervals, okay? But you need to remove infinity, all right? So those intervals, or those intervals, or those intervals. So why is that true? Well, simply because when you take any open set, so if it's unbounded, then it's already going to be kind of contained in one of these intervals. And if it's bounded, then it's going to be contained in an intersection of intervals like this. So maybe, an interval like this with an interval like this, okay? And so that's sort of how the Borelness here is related to this rather specific choice of intervals. Okay, so that's kind of how, and so you still have things to do to get past that, but that's kind of the intuition. And why is this characterization of Lebesgue measurability kind of more insightful? I won't say it's simpler because we have Borel sets here rather than intervals, but I claim that it's more insightful. And the reason that I claim it's more insightful is if we think about the characterization, all the possible characterizations of continuity, characterization of continuity where F is continuous if the pre-image of every open set is open. Okay, so I'm assuming in your analysis course you saw this, right? That you saw that there's many characterizations of continuity, and this is one, right? So the pre-image of every open set is open. Okay. And so this characterization of continuity seems to bear quite a significant resemblance to this characterization of measurability, right? So you're looking at pre-images of the pre-images of sets of certain with a certain character. Here, Borel sets, and here, open sets. Okay. All right. All right, so good. What other properties do measurable functions have? All right. Now, when we talked about the Riemann integral, we talked about approximating our functions as a way of defining the integral, right? So we approximated our function above and below by step functions, okay? Now, when we build the Lebesgue integral as we're doing now, we also use kind of approximations of our functions, but we use approximations by not step functions, but by functions which we'll call simple functions. So let me tell you what a simple function is. Okay, so these should be thought of as being the analog for the Lebesgue integral of simple functions for the Riemann integral. Of step functions for the Riemann integral. Okay, so a function f from I to r is simple if so f can be written in the following form. So it's going to be a finite sum j equals 1 to k. So there's going to be some constant Cj, and then there's going to be a characteristic function, and I'll tell you what it is if you don't know. Okay, of some measurable set aj. Okay, so let me just say what all of these things are. Okay, so for C1 up to CK, a real number, A1 up to AJ, these are the big measurable sets, subsets of I, okay, and where chi sub A is the characteristic function of the set A. And so what that means is that it's equal to 1 when x is in A, and it's equal to 0 when x is not in A, right? That's the characteristic function. Okay. All right. And so what this is saying is that f is a sum of a finite sum of functions that are constant, okay, and you know, so on the set aj, this function takes the value cj for points in aj and 0 for points off aj. All right. And so it says that f is a finite sum of these things, right? So it's a finite sum of functions, each of which is constant on some measurable set aj and 0 outside aj. Okay, so we can assume without loss of generality that sets A1 up through AK are pairwise disjoint. Okay, meaning the intersection of any two of them is empty, and so then the idea, if they're pairwise disjoint, is that on the set aj, the function f will take the value cj because there's no other points in aj which will be in any of the other sets aj. So it's easier to maybe visualize in this case where these are pairwise disjoint. And you know, the reason that that's true is that if they're not pairwise disjoint, then you just partition your sets aj, you know, into bits that, you know, don't intersect any other set. Okay. Okay, good. So that's what a simple function is. Okay. Okay, so we had this function f, which was a function from 0, 1 into r. Okay, and that was defined by being 1 on the rationals and 0 on the irrationals. Okay, and this is a simple function. Okay, just because it's 1 on that set, which is measurable, and 0 everywhere else. Okay, good. Okay, so what is the connection between simple functions and measurable functions? Okay, so that's an important part of the construction of the Lebesgue integral. Okay. Okay, so let f be a function defined on some interval. And here I'm going to assume that it's extended real valued, but non-negative. Okay. All right, then let me make 2 equivalent statements. Okay. One is that f is Lebesgue measurable. And the other, okay, says there's a sequence of simple functions that converges to f from below pointwise. All right, so let me spell that out. Okay. There exists a sequence fj of simple functions such that okay, so first fj of x is less than or equal to f of x for every j and every x. Okay, so these the graphs of these reside below the graph of f. Okay. Fj plus 1 of x is greater than or equal to fj of x. Okay, so this for each fixed x, this is an increasing sequence. And c, the limit as j goes to infinity, fj of x is equal to f of x. And this holds for every x. Okay, and so this is so this says what I first said in English, right? So it's a sequence that approaches f from below. Okay, it's an increasing sequence of functions, and it converges pointwise. Okay. All right, so I'm saying 2 things here. I'm saying that first, if f is Lebesgue measurable, then it can be approximated by simple functions in this way. And I'm also saying that if you have a sequence of simple functions in this way and then take their limit to be f, then that function will be Lebesgue measurable. All right. Okay, so then now we can actually define the Lebesgue integral. And first we define the integral for non-negative extended real valued functions. Oh, so sorry, I apologize. first, I am going to define the Lebesgue integral for simple functions. So that's it's clear how you do that. So let f be a simple function. Okay, so therefore, f is a sum like so. Oops. Okay, so it can be written like that for some real number C and some Lebesgue measurable sets AJ. All right, so then the Lebesgue integral of f is, and I'm going to write it as the integral over I of f d lambda. Okay, that's the notation I'm going to use for the Lebesgue integral, and to distinguish it from the Riemann integral, which we wrote as the integral of f of x dx. Right. And this has the obvious definition. Okay. So I think for the purposes here, I think I want to, in order for this to make sense, this to be like that, because one of these sets AJ might have infinite measure. Okay. Okay. And so the definition of the integral is kind of clear. So I know that on the set AJ, I take the value CJ, okay? Or let me say that differently, because I'm not necessarily assuming that these things, I'm not necessarily assuming that these things are pairwise disjoint. So this function, okay, the integral of this function, because it takes the value CJ on the set AJ, should just be the value CJ times the Lebesgue measure of AJ, right? And then, the integral of this is going to be the sum, because I'm now apparently going to ask for the integral to be linear. Okay, so that's the integral of a positive simple function. All right, now I'm going to start where I started a moment ago. I take an extended real valued measurable function. Okay. Then, okay, the integral over I f d lambda, the way I define this is I define it to be the sup of the integral over I of g d lambda, where g and so I should have said here, although these simple functions up here in this construction can be taken to be non-negative valued. Okay, where g is a simple function, such that g of x is less or equal to f of x. Okay, And so I kind of have in mind now this characterization of simple functions that they can be approximated, or sorry, of measurable functions is that they can be approximated by simple functions from below in this way, okay? So I'm going to choose one such simple function g and calculate its integral, and then I'm going to define the integral of f to be the soup of all such things. Okay, and so you can imagine, for example, that you would do this by taking a sequence like so, okay, from this fact, and then for each sequence fj, calculating this according to that rule, and then taking the limit as j goes to infinity. Okay, and that'll get you the same thing. All right, so that's the Lebesgue integral. Of f. Okay, so now because I'm restricting here to non-negative functions, this is always defined. Okay, so the only requirement that I have on f here is that it be Lebesgue measurable, and as long as I do that, then this is always defined. It's just, that soup may be infinity. Okay. All right, so for positive functions, measurability is equivalent to sort of integrability in this sense. Okay. All right. Now, that's the case where f is a non-negative valued. Now, the arbitrary case, we take just like we did when we built the Riemann integral. So we started with the on arbitrary intervals, we started with the Riemann integral defined to be positive, and then when we defined the integral for an arbitrary function, we took the positive and negative parts and defined the integral to be the difference between the two integrals. So we're going to do the same construction here. So we start with a measurable f. Okay. All right, define in the way, just the way that I did before. So f plus of x is going to be the max of f of x and 0. All right, so when f is positive, it's f of x, and when x is, when f of x is positive, it's f of x, and when f of x is negative, it's 0. Okay, and then I'm going to take the negative part in the same way. Okay. All right, so both f plus and f minus are non-negative valued. And, you have to show some things here. You have to show that if f is Lebesgue measurable, then so are each of these. And this follows from properties of measurable functions that I'm not going to outline here. Measurable functions are very, very flexible in the sense that they're closed under many different kinds of operations, including taking soups and imps like I'm doing here. Okay. All right. All right, so then, if either of the integral over I f plus d lambda, okay, which makes sense, or integral over I of f minus d lambda. Again, both of these make sense because f is f plus and f minus are positive or non-negative. Okay, if either of these are finite, okay, then the Lebesgue integral of f. The terminology we use here is that this integral exists. Okay, and we write integral over I f d lambda to be integral over I f plus d lambda minus integral over I f minus d lambda as the Lebesgue integral of f. Okay, and we allow for the possibility that this could be infinity if this is infinite and this is finite, or it could be minus infinity if this is infinite and this is finite. What we don't allow is for both of these to be infinite. Okay. If both integral over I f plus d lambda and integral over I f minus d lambda are finite, then f is Lebesgue integrable. Okay, so that's the terminology. Okay. And the integral is exactly as it was above. Okay. All right, so that is the construction of the Lebesgue integral, and it's also the definition of an important class of functions, which we call Lebesgue integrable. All right, so I think I'll stop there, and we'll talk more about some important properties of the Lebesgue integral next time.